This section, section 13.3, concerns the concept of pressure and also of Archimedes' principle. Let's first of all define pressure. Pressure is defined, P, capital P is used to symbolize pressure, is defined as the force we apply divided by the area over which that force is applied. The units of pressure are the Pascal, and the Pascal is by definition, it's abbreviated PA for Pascal, and it is by definition 1 Newton per square meter. So if we have a pressure of 1 Newton over an area of a square meter, that's a pressure of 1 Pascal. By contrast, you can say, well, what is atmospheric pressure? How much is the atmosphere pushing on everything? And atmospheric pressure at sea level is 1.013 e to the 5th Pascal. In other words, we could approximate atmospheric pressure very accurately to within at least 1% by just saying that it's 1 e to the 5th, and this is what you are responsible for remembering. The atmospheric pressure is 1 e to the 5th Pascal. That's 1, and then move the decimal point 5 places, 1, 2, 3, 4, 5. So we see that it's 100,000 newtons for every square meter. So on a square meter, the atmosphere is pushing at 100,000 newtons. In fact, if you take your hand and think about your hand, I'll draw a hand here, but I really want to just look at the palm of your hand. It measures about 4 inches by 4 inches. And if you think about the pressure that's on this 4 by 4 inches, then it's really considerable. In fact, the way to think about this atmospheric pressure is when you hold your hand out, you're supporting a column of air that goes all the way out to outer space. Now certainly you can say, well, why doesn't my hand move downward? Well, there's an equal pressure beneath your hand that's pushing upward. In fact, it's slightly greater, just ever so slightly greater at the bottom than it is at the top because it's a little bit deeper. It's just like in water, things tend to float. They have slightly greater pressure at the bottom than they do at the top because of the thickness. But on the average, they're going to balance each other. So your hand doesn't feel that pressure because you have a pressure downward from atmospheric pressure, but the atmospheric pressure also comes around the sides and pushes upward with an equal and opposite force. Therefore, that's balanced. Now, if suddenly there were a vacuum here underneath your hand, you would be really hard-pressed to support the atmosphere that's pushing down just on the palm of your hand. So in general, we can say that atmospheric pressure is 100,000 newtons per square meter. And that's a good approximation, and we will use that again and again. Pressure in a fluid is a combination of two things. The pressure in a fluid is the pressure at the surface plus the pressure that's further down in the system. Let me show you how that arises. If I think about a fluid here in a tank, and I imagine that I have an area down here, then there are two things that are pushing on this area. First of all, there's the water that's above this pushing down, but then there's an additional force of the atmosphere pushing down on the surface of the water. This area has to support both of those. So in general, we can say the pressure at some depth is equal to the pressure at the surface, that's your surface, plus rho times g times h. Now, where do we get this rho gh? Well, if I think of the rho gh I can think of rho times h times an area divided by an area. So let me rewrite this and show that this is the same as rho times an area times h divided by an area times g. Well, the area times the height in the liquid, area times height, is the volume. The volume times the density is the mass. So this term right here is the mass. That's mg. So this is the force, which is the force per unit area. So now what you can easily do is say, well, pressure is force per unit area. Force is m times g divided by area. The mass is rho times a times h. I should have written a small h there, excuse me. A times h. And the area cancels the area, and I get rho times g times h. And this tells us what the pressure is further down inside a fluid. We can use pressure gauges like water and columns of mercury to measure pressure, for example, because of this. And the way we do that is we take something like mercury, and we fill a tube with this mercury and then put it in a little puddle thing of mercury like this, where the mercury can be pulled downward. And we make this tall enough so that this mercury that's pulling down here is going to be very, very heavy. So it's going to push down and leave a vacuum at the top. Until what happens? Well, the atmosphere pushes down here at this point, and the mercury is pushing down at this point, and those pressures have to be exactly the same, the forces per unit area. Therefore, the height or the measurement on the side of this will give the atmospheric pressure. If the atmospheric pressure is greater, it will, you could say, it pushes the fluid up into here. And of course, you can also say that this column of mercury is exactly balancing the atmospheric pressure. Now, whether we use water or whether we use mercury is immaterial, except for the point of, that the mercury is 13.6 times as dense. So for water, we have to use a column that's enormous, and you can't carry the thing around. A point that I want to make relative to that is if you have a well, so here's the earth, and you have a well way down here to an aquifer, and you say, well, I want to suck this up, bring this water up by using a vacuum to suck this. So I have a pump that sucks in this direction and brings the water up. Is this going to work? It turns out that atmospheric pressure is about equal to 34 feet of water in balancing it. So if I put 34 feet on a perfect vacuum, the water, the atmospheric pressure cannot push the water up higher than 34 feet. So you can never suck water up or have a vacuum over the water that will bring it higher than 34 feet. And with mercury, it's about 113.6 times as much. You can easily sit down and compute, like in your homework, what exactly this figure is in terms of feet, and it's a good exercise. So pressure gauges can use water or mercury, or they can use discs like this, and this has a certain pressure in it, and you have a device here where this is attached and a little very sensitive hand, and this hand moves when the air pressure pushes in or lets this pull out for this little diaphragm with a sealed container here, so you can measure the pressure from a device like that. Now, Pascal's principle states that the pressure that's applied to an enclosed fluid is transmitted equally to all parts. So whenever we have a fluid inside, that pressure is transmitted the same in every direction and in all parts. Now, if it becomes very deep, then of course the depth we've already discussed here, and the pressure does increase with depth, but at a relatively the same height. Pascal's principle will say that pressure is going to be equally done. Now, we can use a very simple device to lift heavy objects, kind of like a lever. And I'm going to use that principle to show that the force per unit area or pressure in one place is equal to the pressure in another. Let me move the paper up here and look at a car lift. This car lift is going to be designed so that this is a very small tube here, and this is going to be all filled with oil. Then over here we have a piston. This piston can, of course, support something here like a car. We can say, well, how can we support this much? Well, if you think about this piston, this car is exerting a pressure over this whole area, and if this piston is large, then we end up with a pressure, which is this force per unit area. Let's call this the side 2. So this would be force 2 over area 2. Well, if I will have the same pressure at the same point at the point over here, and let's call this area 1 and force 1. So we know now that the pressure here is the same as the pressure here, so it must be equal to F1 over A1. Well, now if A1 is very, very small, then F1 can be very, very small. So if we make this 1/100th of this area, then in fact this force is 1/100th of this force here. Very similar to using a lever or pulley system to achieve what is called mechanical advantage. And therefore, this principle can be used to lift very, very heavy objects by using a very small area here. Of course, what you have to do is kind of like with a lever. When you recall when you have a lever, if you want to lift something very, very heavy, you must have a long arm here and a short arm here to lift it with. And likewise here, you have to have a very small area here and a very large area here. So you're going to push down a lot of fluid. This is going to go real, real far to just get the car up a few inches. So normally what you're going to do is you're going to put more and more fluid in here as you move that along. This is what is called a hydraulic lift. The final thing that I want to discuss with you is what is called Archimedes' principle. Now, Archimedes' principle you've all heard of since the early grades. He is the one that was in the bathtub and figured out how things are buoyed up by a fluid. So let's imagine that we have a tank here, and we look at some object. We can say, okay, this might be brass or something like that. What if we weighed it? What if we put it on a weight, hung it on a scale, and looked at what it weighed while it was in water? Well, it weighs much less. Why? Well, gravitational force is pulling down on it, and you have the water actually buoying it up. Well, it was Archimedes that figured out, and he lived between, I've got the dates down here in your notes, between 287 BCE and 212 BCE, and he was able to show that the force buoyant was equal to the weight of the displaced fluid. So, whatever this object displaces, in other words, the water that would be contained in this volume, this water, it has a certain volume, and we know what the gravitational force of that water would be the density times the volume, and that would equal to the mass, because density is equal to mass per unit volume. So we can figure out what the mass is of the water if we know the volume, and we can say, therefore, this mass times G, M times G, or rho GV, would be the upward force. So the brass is going to weigh less by virtue of the fact that you have the weight, the normal weight of the brass in air, and then you have the buoyant force that's here. A perfect example of that is a human. And since a human displaces about their specific gravity is about the same as water, It turns out, therefore, that the volume of water they displace is equal to their own weight. If you fill a tub up, and we've got a tub here, and you get in and submerge yourself, and imagine that the water was exactly full before you got in, and then you could collect this water and figure out exactly what that volume was, in other words, the volume that you had. The weight of this water is the buoyant force forcing upward, but the weight of you is pushing downward. If you weigh the same as the water, then in fact it turns out that this volume that's going to be sent out is the buoyant force, and therefore it's the volume of your body. Your body is going to exactly float in here because the downward force of gravity and the upward buoyant force are going to be exactly the same if your specific gravity is 1. And you should be able to use this to calculate what the upward force is for a given object. So we can say, what is the buoyant force? The buoyant force is this principle right here is the weight of the displaced fluid. Now, what is the weight of the displaced fluid? The weight of the displaced fluid, I'll put it over here, is going to be the density of the fluid times the volume that's displaced. So what you want to do is calculate what the volume is of the object that's under a fluid, and then multiply by the density of the fluid, and that'll tell you the buoyant force, which is the same as the weight of the displaced fluid.